This is your podcast number 3 for Unit 2, and these are the chapters that I will be covering. So this pretty much should cover everything that I'm covering for Unit 2. And these are the subjects that I will be covering. If there's any questions or any subtopics that I did not cover in these podcasts, then please let me know during class and I will cover it during class, alright? So please refer to your objective sheet for Unit 2. So this is what we call a phase diagram, and this is a phase diagram for H2O. And H2O tend to be different from most materials. It is a very unique material, and so I'm going to talk about H2O first and then talk about how majority of other phase diagrams look like, which isn't too different, so it should be mostly translatable or transferable. Here is my x-axis in temperature and my y-axis being the pressure. Let me first give you a little bit of vocabulary before I move on. Solid, liquid, and gas, you guys know what that is all about. You have solid at a high pressure, low temperature. So at high pressure and low temperature, the water is a solid. And that makes sense because if I had a small container and it's high pressure, as in there's lots of particles around, and the particles are slow moving, these molecules are going to stick to each other and become a solid. Versus if I have in a liquid medium temperature and high pressure, as in there are lots of particles around, but the particles are faster moving, they're going to tend to become a liquid because they're faster moving. Even though there are lots of particles around, they just have the momentum to become a liquid. And so this is a liquid. And in a gas, this is a solid, liquid. And in a gas, the particles are really spaced apart because I have low pressure. And they are fast moving. So they tend to be a gas. Let me give you some vocabulary. Solid into liquid is what we call melting. Melting, in the more scientific term, is fusion. Okay, fusion means melting. The opposite way, we call it freezing. And now we're going to call it solidification. This, we call it evaporation or boiling. But we're going to call that in this class vaporization. Okay. The opposite way, we call it condensation. And we're going to keep it the same as condensation, gas turning into a liquid. When a solid turns into a gas, we call that sublimation. Let me write that because it doesn't show up very well there. Sublimation is when a solid turns into a gas. The opposite way, called deposition. So over here, this opposite way is called deposition. Deposition is when a gas turns into or goes into the solid phase. So this slide is looking a little bit messy, so I'm actually going to erase all these vocabulary words in order to explain the phase diagram. Please have this in your notes before I erase it. And I am erasing it now. So, I know that if I am at a low temperature and at a medium pressure, that my water is going to become a solid. Okay? When I am at a low temperature, but I start increasing the temperature, it's going to start melting and it's going to become a liquid. What does water look like right on here? So I'm going to call that my point A. What does my water look like at point A? It looks like slushy, or it looks like ice water. So when I have water with ice in it, I am at 0 degrees Celsius. Water is going to be 0 degrees Celsius no matter how much water I have, because I'm in this between phase of a solid and a liquid. So at this point, I'm gonna have 0 degree at sea level. My ice water is going to be at 0 degrees Celsius no matter how much ice I have in it. It could have lots of ice and it could have a little bit of ice, but as long as I have a liquid and an ice in one container, it's going to be at 0 degrees Celsius. So now, if I was along this line, what does my material look like? Over here. And so this is going to be my point B. Point B, what does my material look like? It looks like boiling water. So you have both the gas phase as well as the liquid phase. So it looks like boiling water here. And that's why it says normal boiling point here. This is all boiling. This is the boiling temperature at specific pressure, or at varying pressure. At varying pressure. So this is all the boiling point. These are all boiling points. Temperature at which the water boils at varying pressure. So over here, along this line though, what does a liquid look like, or what does the water look like? This is my C. Okay? Water looks like kind of like how it may look like in the Arctic or the Antarctic. You know how like there's like a plain of just ice, and then you see like this wind, the gush of wind, and it's carrying these water vapor. It's not liquid, it's not water, but it's just water vapor, like ice that just become a gas phase and just kind of like a wind of water, or a gust of water, right? And that's what it looks like. So along that line is where the vapor as well as the solid ice coexist. And this is where, along this line is where the gas, the vapor, and the liquid coexist. And along this line is where the solid and the liquid coexist. Okay? Or exist at the same time. This water phase diagram is slightly different from the CO2 diagram in that the water diagram always has this slant right here. This arm of the phase diagram is slightly slanted towards left. Slightly slanted towards left. So in other words, if I am at 0 degrees Celsius, so I erased the table a little bit so that I could draw on this a little bit more. I want to talk about the phase diagram of H2O being slightly different from most materials. So let's say that I am at about -2 degrees Celsius. So I'm at -2 degrees Celsius, and I'm going from low to high pressure. So over here I have my -2 degrees Celsius at low temperature, and I am going to go up. And you can see that the water would turn from a gas into a solid. And that makes sense because, there's a lot of pressure onto that gas of water. But if I get it into a high enough pressure, water turns back into a solid. So at high pressure, the water exists in a liquid. So that makes sense because if you have, so at high pressure, meaning which also equals to high density, at high density, water is a liquid. So if you have ice water, you know that the liquid is in the bottom and the solid is on top because the liquid is more dense than the solid ice. This also helps in that if you are in a river or an ocean, this is my land, and here's my land, mountain, and here are my fishes. When ice starts to freeze, it starts to freeze from the surface of the water, and the ice will float up. And so here is my layer of ice. Here's my layer of ice. But the fishes are happy down below because they can still swim in the water, versus if this was my ocean and here's land. If solid water was more dense, you would have blocks of ice down below. And eventually, if it's cold enough, it will freeze from below and freeze the entire water from below, leaving our fishes dead. Dead. Or our fishes are dead. Are dead, right? They're dead because they're stuck in the solid liquid. So it's great that our H2O behaves differently than other materials, because if it was a solid that is more dense, our oceans would freeze over, right? Here's a diagram for CO2, and this kind of represents most materials. In that, not the numbers, not necessarily, but the shape of the phase diagram. And as you can see, this arm is slightly slanted towards the right. Slightly slanted towards right. So if I start at this temperature and I raise the pressure, it just turns into a solid and remains a solid. So most material under high pressure will become a solid, but water is unique in that it actually turns back into a liquid when it is at high pressure. And that's all I wanted to cover with the phase diagram.